let me know when you can see my screen. Any of you can just shout out, no problem. And if you cannot see my screen, let me know that as well. Guys, can anybody see my screen?
Not yet.
Not yet? All right. Let's stop sharing again and start sharing again. Let's see if this works. Can you guys see my screen now?
It says you aren't sharing.
I'm not sharing. That's interesting. Can you guys see my screen now?
Yes.
Perfect. So thank you for waiting for me. I was locked out of my lab and I had to call the PD and a whole lot of things after that. Anyway, so first of all, let me actually get you accustomed to the final exam format that we have. Now, be sure that the problems are might or might not be the same. So we are going to go through the various problems that we have, but this is a 2 hour long exam and this has the highest weightage of all the other exams that you have. So just in case you are, planning to pull up your scores a bit, this is the exam for you. So you will see immediately that there is a statistics problems. Now we used to have three big statistics problems that has been reduced down to just one problem. And that is also like all your tables and everything will be given at the back of your exam. All you need to figure out is what type of distribution you should use for each of these types, right? The second problem is again a derivation problem. Now we are also going to go through this derivation problem so that we understand what exactly we are supposed to do to derive this and how much of it you are going to derive and what are the points associated with the steps, right? So unfortunately, I actually was told by a couple of students that they are going to have their iPad, but we don't have our iPads. So I'm going to use my mouse and try my level best to actually write anything or everything that is there. But other than that, I should not be having too much of problem explaining the process of it, right? So I'm going to also give you the rubrics. So lucky or unlucky, whatever it is that I am actually going to grade your exams this time. So I'm going to give you my rubrics and exactly what we are supposed to do for that. And CLT is definitely going to be there. This is your third question. Now, this type of CLT problems, any type of CLT problems, they are going to come with no surprises. First of all, it is a Gaussian distribution. So even if it is not mentioned out here, yes, it is a Gaussian distribution. And you have a couple of things that you can check for. You have the average lifetime given, sample space between so and so. So again, CLT is also central limit theorem is also a very stepwise process. Like if you go wrong in one of the steps, you obviously receive partial points. Even if your answer is, again, you know how I work, even if your answer is completely wrong, you are going to get just 1 points deducted from your final answer, and other than like the entire steps being completely wrong. Um, this one is again also a different kind of statistics problems that we introduced in the last semester. We are not probably going to have this many statistics problems, but if you are revising, I would advise you to only concentrate on Z, T, and chi distributions for I'm going to show you the tables and I'm going to tell you exactly what to revise so that you don't get confused. This problem, I don't know whether this has been done in the class or not, but if it is not, I'm going to teach you how to do it just in case Dr. D changes his mind and wants to give us something funny. So you should be able to work that out as well. I'll talk about when I solve it. And this one is again, it's kind of like another, uh, you know, another type of statistics problems. I don't know why they have given so many, but I mean, you can solve this by CLT as well. So it's a very neat Gaussian distribution, scored higher than 70, in between 70. This can be scored very easily by CLT as well. And those are the 6 problems you have. So you can see that the final exam for the last term was very different. Now, what is going to be very different for you guys is that you guys going to have a little bit different. Since some of us have done something interesting, we are going to obviously expect a problem from our normal statistics. So I'm not going to go too much in details of that, but I'm going to actually go back to my original screen and actually show you that we had 6 total problem, but in the 6 problems, you had different parts to it, all right? So it's 6 or 7 problems, depends. So from the course material, what you are going to be entirely concentrating on is this table. And I know Dr. D has gone multiple times over this table, but I'm going to still make you aware that if you are revising everything from this table, concentrate only on Gaussian, first of all. So Gaussian random variable, the variance is known. Gaussian random variable, the variance is unknown. And Gaussian random variable for unknown mean. These are the 3 types that you have to basically concentrate on for your final exam. Now, out of these 3, if I'm not very wrong, T distribution is the least likely for you to be getting in your exam. You are definitely going to get one problem from Z distribution, no matter what happens. You are going to get one problem from the chi distribution. Now, chi and T sometimes, kind of keeps varying. So sometimes you can get a T, sometimes you can get a chi. But overall, the chi and the T distribution is like equally likely. So you have to know Z distribution. T distribution, it's going to come with its own flavors of, we're going to talk about it again when we talk about Z. And there are 3 very distinguished features for each of these different types of Gaussian random variables. So you're going to be very easily identifying each of them. So don't worry about that because we are going to talk about that. But the rest of the things are already given. None of the tables, you don't need to carry any tables, no formulas, no nothing. You are already aware of that, so I'm not going to go over that. Okay. So what we are going to do today is that, first of all, we are going to go over the basics of how my rubrics works. I know you probably already know how to solve these problems, but then I'm going to make aware so that you score the maximum points. This is, again, first of all, this is a problem from statistics. We are going to go over a problem from the derivative principles, exactly why this is given to you, why are you trying to solve it, what part of the chapter is this, etc., etc. Then we are going to go, I don't know why a lot of people have got this specific problem as incorrect in the midterm exam. So we are going to go a little bit over that. And I'm not going to concentrate too much on the midterm problems other than the fact that if you specifically tell me, okay, no, I need these specific problems done. A fair coin is tossed. Again, this is a very straightforward CLT problem. This is a Jacobian problem. Now, even though Jacobian has been done or not done or whatever, this has been given to you in your homeworks. So we are going to try and solve that and see if we score perfectly on this one. And then, of course, this problem will be there, or some of the other variations of this problem will be there. Okay, so I mean, obviously the function may be different, like the fxy of xy may be different, but I mean, maybe the same, I don't know, because that part, I mean, usually when we set the paper, I'll if we are setting it like 50-50, this time we are probably doing it 50-50. Like last time, Dr. D kind of completely did the paper on his own, but this time I'm trying to do it 50-50. So sometimes the functions he will actually variate that, but the type of the problems mostly kind of loosely sits on me. So again, don't take my words for exact like the Bible of the exam, but what I'm trying to give you is how to score. Okay, so let's get started. And if you have any questions in between, let me know. Shout out to me, whatever. All right. I didn't care about the title and everything anyway. So my exams are over, by the way. I kind of very gracefully passed my exam. This was one of my very, very important PhD exams and my PhD milestone. So you can bother me at any time, at any place, anywhere, starting from now on all the way to the exam. Don't hesitate. Even if it's 4 a.m., you see me online, I don't really mind answering questions. Yes. So this problem, uh, the so when we introduced this problem, we knew that there was a very basic step that was missing, that people get too much excited about the hint that we have given for part B, and they assume that this entire problem set is basically a chi distribution. Okay, so what I'm going to tell you is this trick. Okay, so the trick is to basically go and look at your tables. So your tables will be, just enable the editing. It'll be easier. My life will be easier. You will have tables of integrals given to you. Last time I was not allowed to give you the tables of integration and differentiation. This time I am going to make sure that you have tables of integration and differentiation and everything else already at the back of your exam. So yeah, coming back to the statistics problem, go back and look at your table. Okay, sometimes the table might be given. Most of the times the table is, oops, oh, this is test 2. No wonder the table is not there. I'm so sorry. Yeah. So most of the times, again, I will give you this table. So when you get a statistics problem, go back and check the first part, because there is going to be a z distribution. So you have to look out for a z distribution first. This is how, and these are not, again, very knowledgeable steps. These are steps on how you can score and how you can avoid making mistakes. So go and look at for z distribution. There has to be one problem for z distribution. So the part A, read the part A and see what you can find out though, right? So the part A says that the lifetime of 225 bulbs are given. So N is given as 225. And we have a sample variance and a sample mean given. So the mean is 223 and the sample variance is 100. Now the first part of the question says find the 95% CI for mean lifetime. So 95%, so first of all, a couple of things going on out here. So we are trying to find out the mean, right? So the variance is kind of already given to us. So go back to your table and see, okay, we are trying to find out the mean. The variance is given to us. So what are the different types of we can associate with that? So the number one is Gaussian with known variance, right? Non-Gaussian is not a problem, because just scratch this out, because we are not going to give you any non-Gaussian problem. So the only other thing that you can actually get around with is a known mean, right? So you immediately know that, okay, we have to find out the mean. We have variance given for us. So this is a z distribution. So the next problem, find out the 95% CI for a variance of lifetime. So the variance is supposed to be so what we are trying to do is to find out for the variance. So then we have a missing mean there. So then again, from the hint, people kind of figured out that this is a chi distribution anyway. So why is the chi distribution kind of given to you is because sometimes the entire table cannot accommodate certain values. And this was a problem again straight away from your homework. So another good thing about the statistics problems is that there's a high possibility for you to get this straight from the homework. So if you revise your statistics problem straight from the homework, you are going to be good. Because we are not going to vary it too much of, I mean, the numbers might be a little bit different, but it's not going to vary it too much. Yeah. So, okay, how to solve that, right? Let's go get into that. So the first part is 95% confidence interval. Well, so the first part is part A. Now, for part A, it's a Z distribution. So if you are starting a part, I would say start your part with saying this is a Z distribution or a chi distribution, or what type of distribution you are considering for the solution for the problem, right? And now you are going to obviously use the formula for the Z distribution. I don't have the formula out here in the screen. So I'm just going to use my intuition. If I'm wrong, please don't screw me. So you have a value called alpha, all right? So this alpha value, very mechanically, again, I am more than happy to explain all these distributions to you because I've derived each of them when I was teaching. So you have 95% confidence interval. Now you have only 2 days left for your exam, right? So shortcuts. So 95% confidence interval means 0.95, right? So now to find out the value of alpha, what you do is you subtract the 0.95, all right? And obviously there's a logic behind it. We are not doing it just illogically. And then you divide it by 2, okay? So you have 0.05 and that upon 2, okay? And some of the students were sneaky because they are, one step ahead of me, which is great. I mean, I don't mind that. They are like, oh, okay, hang on. This guy is already trying to guide us towards a specific number. If you see like my cursor right now, it's kind of guiding you towards a specific number. So this might be something that I'm interested in, these numbers. So they kind of figured out, oh, okay, this is 0.025. I mean, if you are in, doing that kind of math, that's fine. But that's exactly how you find it out, 0.25. All right. So first of all, this is step 1. All right. So I'll be looking for your alpha. Okay. Now this step does have only, like, if your entire problem is say 15 points, okay, I'm just giving an example. This step is hardly going to contain like 3 or 2 points, okay, because like this is just basic math, but sometimes students go wrong in it. So I usually kind of look at alpha. So once you look at alpha, you're going to go to Z distribution. So your Z of alpha, you are going to write the value, whatever of Z of alpha you have. So out here, you look at the table and you come up with this value. So this value is going to come from table. Okay. So once you look at the table, this table lookup also has 2 points or very less, like 2 or 3 points. It depends on like, how much point distribution is there. So either a 2 or a 3 points, depending on how much of weightage. Okay. So after that, you are going to write your main formula, and you can, some people directly start writing values. But what I would say is just either you can write the formula out if you are not too accustomed to that, or you can actually write it out like, n is equals, what is n? 225. Oops, 225. So you can directly start, writing your values out here. So this is, oopsie, 225 minus your Z distribution, 1.96. I think it's the variance 10 upon, like this is just a generalized formula for it, So I'm not like memorizing anything. This is just how the formula works. And then you have the other part of it. This is 225 plus whatever value that you have, 1.96. The variance. So this is all a part of the formula. This is very easy stuff. Again, if you go wrong in the calculation of these stuff, only 1 point will be taken away from that. Other than that, you're going to have basically, the entire points. So, oh, this is a comma, by the way. So these are the 2 parts. So for both the parts, so if again, just the part A has, let's make it even. Let's give it 20 points, right? So the part A has 10 points, the part B has 20, another 10 points. So if I have 2 or 3 points for here, say for example, the first step has 2 points, the second step of looking up the table has 2 points, the rest of the points, the rest of the 6 points will be out here. All right. What about part B? So the part B has, again, you have 95% confidence interval for the variance. So the variance is already given to us. So now we have an unknown mean that we are trying to look for. So then, again, at the beginning of the problem, write chi distribution, right? Because that's what you're using. And then the chi values are already given, so you might not just repeat that. In either case, I mean, you can repeat it if you want to, if you feel like, again. So people usually start writing the bigger formula. And remember that this is the chi distribution goes on n minus 1. So n minus 1, that is 224. And again, whatever the formula reads out. And where do you find the formula for all these things? Well, you find the formula in this guy. So I'm using basically the last step and the first step of this entire distribution, of this entire table. So then just write it out and calculate it by your calculator. That's all it is. It's as simple as that. Again, sometimes people go wrong in the calculation of it. So you know that I don't really care about the calculation, so that's fine. If you go wrong in punching numbers in your calculators, I really don't care. So again, write the other part, and then that's kind of it. All right. So this is chi distribution. You have the chi distribution tables given to you. So if you want to mention the chi-square tables out here, mention the chi-square tables out here. So the lookup part will always have points. So the chi distribution lookup, I've kind of already done that for you. So there's not going to be any more points in there. So this one is going to have all the 10 points out here because the values are already given to you. If the values are not given to you, you'll have 2 or 3 points to find alpha. You'll have 2 or 3 points to look at the table. And you'll have majority of the points to put the formula in and calculate and find out the numbers. So that's the statistics for you. It's standard for Z distribution, T distribution, chi distribution, any distribution. Now, the important point that you have to note that why did I not use a T distribution out here? I mean, obvious factors are that it's not kind of a T distribution problem. But had it been a T distribution problem with an unknown variance, you see, there's a difference between Z and T distribution if you talk about it exactly mechanically. So mechanically, again, T distribution usually is applied to those distributions with very small n. Now the n out here is, I mean, it's not great, but I mean, it's 225 for us, so it's not that small, you know. So we use a Z distribution for that. T distribution could also be an approximation, but it's not going to be a great approximation. Remember that we are always trying to kind of find out the estimated value, although it's not kind of mentioned out here. It's kind of like I'm 95% confident that the mean that I'm so sorry. The mean that I'm trying to find out, or the whatever I'm trying to find out, I'm 95% confident, or 96% confident, whichever way it is. So these are all estimated values. So you can very well use T out here, but it's going to be incorrect because it's not a small distribution. All right, so those about the nitty-gritties, you know. Let's actually keep going. If you have any questions, stop me in between and ask. Now, this problem, sometimes Dr. D, what he does is this. Now, I have to make sure that I kind of explain this very well. Sometimes the X hat, I mean, I'm going to tell you where this is coming from, but I mean, just let me explain. Sometimes it will be given as, oh, let me see. I'll play around with the equations, and sometimes you'll have, you know, b of y2 and plus c something, you know, something big. And people get scared because this type of expression, they haven't practiced on this, but it's very easy for you to deduce. And I'll show you exactly why. Excuse me. Let's start with why is this even here. So again, remember probabilistic values are estimated values. Estimation is a very big part of probability. I mean, obviously, there is nothing constant about probability, right? So this is one of the, there are many ways to again estimate. There is something called as mean posterior estimation. There is mean squared estimation, and there are various other formats. So what we are trying to actually learn out here is a very, very common format used in machine learning, some of your control applications as well, which is called mean squared error. So the mean squared error, basically exactly as it sounds, it will take the mean and we are going to actually calculate the mean with the expected values, all right? Squared means it is going to have some kind of squaring going on inside. Why? Because sometimes when you take the error, it might actually come out as negative. It might actually come out as positive. So what we are going to do is we are going to take the, kind of the um, absolute value, if you may. Uh, I mean, people often argue that why squaring it and why not taking an absolute value? That's a different argument. That's not required for this exam. So I'm not going to concentrate on that. But that's actually an interesting thing to, observe. And what we are doing basically is this. We have a given, we have a given signal, all right? We have a given equation, we have a given factor, and we are estimating another one, all right? And that is what we are calling as x hat, which is given out here in this equation, right? So we are subtracting that. And what we are trying to find out is this is already something that we have, all right, or we try to achieve. This is given. And this one is the estimate, all right? We have to remember this because this is going to be important for us. So this is the estimate and this is the given, all right? So now, we are taking the mean of that. There's the square. Where is the error, right? So the very fact that you are taking the given and you're subtracting the estimate from that, that kind of generates an error signal, which is called as E. Okay, so this entire expression is called as E. Now, the entire point of the entire machine learning domain or the estimation domain or whichever domain you cover. So that entire domain is based on minimization of this error. Okay, so how do you minimize an error in any system, right? We are trying to actually play around with the fact that we have error in a system and we are trying to variate some parameters in the system so that our error is minimized. All right, what are the parameters that we are trying to verify or variate, right? So we have a given signal, or we have this signal is supposed to be estimated again, right? So we have taken, as an engineer, this is your job, right? You are supposed to design a system or design anything, and then you're trying to replicate it as close as possible to the ideal conditions, right? Which is obviously, kind of a myth. But anyway, that's what our job is, right? So we have estimated, we have taken a signal y, which we know, suppose it's a sine wave or a cosine wave or whatever, and we have scaled it up, and we have kind of linearized. So this is a scaling and a linearization. For those of you who are control system guys, this is linear estimates. So yes, MSE or mean squared error is going to basically work on linear estimation problems. For non-linear problems, again, it's going to become a little bit more complicated, but we are not going to deal with that. What are we trying to do is to actually variate this A and B in such a way that it becomes this X, X hat becomes as close as possible to X. Okay. That is why we take the error. And so the first step is to take the error. All right. The second step is to minimize the error. Okay. Based on A and B. Okay. We are going to talk about what minimization really means. And then, where is my mouse? And then third step is basically to put, what the hell? Okay. Put the estimates, put estimates of A and B. So these are the two estimates back to X hat. So these are the three steps that you have in this problem. Okay. So now these three steps have three different point markings. Not all of the steps have equal points. So for example, again, if this problem, I don't know, if this has 15 points, say for example, finding the error will have 2 points. Minimization will have most of the points, like 12 points or something like that. And putting it back into the equation will have just 1 or 2 points, depends. So the maximum bulk of it is in step 2. Okay. So we are going to go over step 2 very, very, minutely or meticulously for you. Anyway, so the first part is to actually write the expression of error. All right. So that's step 1. So error is x minus x hat. All right. Whatever that x hat is. And you take the expected value of that. All right. But then you have to actually square it because it's mean squared error. All right. So what does that expression look like for our case? Our expression kind of looks like error signal, expected value, open brackets. X is the original signal that is there. We are trying to subtract x hat. So x hat is ay plus b. All right. So it kind of looks like this. Right. So this is the entire first part of the entire equation. All right. You take this correctly, it's done. Now, the part 2 kind of starts in a little bit different way. So you have to, so you can start with this part as well. Okay. So don't get me wrong. People basically start expanding on this entire equation. So let me actually, so people basically start expanding on this entire equation and you can go ahead and start there, right? You can basically just say, oh, this is an a plus b plus c squared kind of equation. So you can expand on it, on this entire thing, find your own expressions, and everything else will go perfectly fine. There is no one way of solving this problem. Let me make this very clear to the students that unless you are going horribly wrong with the entire process or entire equations, like you don't know how to square it or you don't know how to differentiate things, other than that, you can expand on this first step and continue the problem. But your book does it a little bit differently, and Dr. D wants to stick to that. That's why we do it a little bit differently. What you do is you, first of all, start with, okay, great. You can expand on this entire thing. I mean, a better way to do that, let's put it this way, a better way to do that is to, first of all, simplify the step. How about let's take, this is the starting of step 2, okay? Let's take, all right, let's take this x hat, okay, to be just a. What happens then is that your entire error signal, then that implies that your entire error signal is just then basically your x minus a whole squared. Oops, that's not the expression that I'm trying to. So sorry about that. That implies that your x becomes, your error signal becomes expected value of x minus a whole squared. And that implies that if you actually basically expand on this guy, what is going to happen is that you'll get expressions like, this is a squared, right? So I'm just kind of skipping one step and just kind of writing this is x squared minus 2a expected value of x. And you'll see in a minute why am I doing this. Plus a squared, because the expected value operator does not have anything. Now, a couple of things out here. So I'm playing around with the expected value operator. First of all, I have never introduced in my problem sessions, at least till I've taken, I have never played around with the expected value. So expected value is first of all an operator. It will basically slide across. So this is x squared minus 2xa minus plus a squared. So that's exactly what I've put. But then the expected value is only going to work on the random variable. It doesn't have anything to do with the constants. So if a is a constant, the expected value of a is a. The expected value of a squared is a squared. So it doesn't have any effect. So that is the expansion of that, and that is exactly how the expected value operates on random variables. So going forward with this one, if you basically try to minimize this equation of just a, okay? So you are trying to minimize the error, okay? Minimize the error. I'm not going to write it like this. Let's write it a little bit differently. So, whoopsie. Okay, minimize the error with respect to a, okay? That actually means that so what does this imply though? So I'm now actually trying to define the minimization. What it actually means is to basically differentiate the entire expression with respect to a and then equate it to 0. This is what minimization means, okay? So our previous expression, if we want to minimize this thing, we have to minimize e of x squared minus 2a ex plus a squared. So if you minimize this entire thing, you're going to get, so this is the expression from the previous. Where's my mouse? So if you actually take that entire expression in the previous page, what you're going to find out is that the minimum value of a, that's also called a star. This is in our machine learning language, if you may. This is called the optimal value. So a star, or not in machine learning language, it's basically convex optimization or optimization language. It's called the optimal value. So the optimal value of a, if you do that entire expression, is found out to be just the expected value of x. So you start here. You start with that if you have just one expression, that is, forget about the entire, AY and AY1 plus BY2, C, whatever. If you just simplify down to, suppose just if we were trying to variate the x hat with just one variable or one constant in this case. So the step 2 starts like that. So then we proceed. Again, this is like a very stepwise process. So if you don't understand one step, please let me know. Then we proceed to, once you finish that consideration, so now back to the problem. So in the problem, we have, what do we have? The expression is given as x hat is now ay plus b, okay? So had this not been present, so let's actually point out a couple of, had this not been present, this entire problem would have been treated as we have treated it in part 1, right? So the b star would still be the expected value of x. Now to that entire thing, we have added a couple of steps. We have added a linear estimator of y. Y is another random variable, and we have kind of scaled that y, and we have added that, right? So now we are telling, okay, how about this estimation? How do we solve this estimation problem? So the B is basically, so if you look at the pattern right now, you have AX. So we have, let me just, so here's where the students actually make the most mistakes. A is already, so if you have a single variable, if you have a single constant, right, you know that the expected value is going to be E, or the optimal value of that particular thing is going to be the expected value of the random variable. So now what you do is you take the similar pattern and say that, what about B optimal value, right? Our constant out here is B. So what does that look like? That should look like an estimated, the expected value of X, right? So yeah, the expected value of X, but then we do have some other terms out here, right? We have some other terms out here. How do you accommodate that term? Very simple. You write X, which is this expression. So you're basically trying to formulate this expression. And what else is added to this one? You add whatever is left. You're almost trying to take this step, all right, and try and say, okay, my optimal value of B is basically X minus AY, right? That's exactly what is going on out here. So that's the optimal value of B for this specific constant, right? Now you can have any equation from now on. Let's say, for example, you put in, how about this expression, right? So the top one, right? So the optimal value of C will be expected value of X minus A of Y1 minus B of Y2. So that's the pattern that you're going to follow, right? So it's not going to be too hard for you. Even if Dr. D changes and plays around with the expression, you now directly can write this, okay? Based on the observations that we have made so far, all right? Once you find out the optimal value of B, let's move on to actually find out the optimal value of A. Because remember, what we are trying to find out is, first of all, the optimal value of A and the optimal value of B. Why? Because we have to, oops, oh, I cannot do that, never mind. Because remember, we have to basically try and optimize this X hat as close as possible to the, let me actually take my pointer. We have to optimize this X hat as close as possible to this value of X. And we are doing that by variating the A and the B. And how do we variate and change that? We are using the minimization of the error signal that you have with respect to A and B. How do you minimize that? Basically, you find out the error and you basically differentiate the entire equation and equate it to 0. And we are going to do that in step by step. But the first step was a little bit of trick in order for us to basically find out that, okay, if we have a simplified version of the constant, that is the last equation. So say, for example, in the above equation of X hat equals A Y1 plus B Y2 plus C, can you find out the optimal value of C first? Or in this expression, X hat equals AY plus B, can you find out the optimal value of B? And that's exactly what we have done. So after that, all right, I may run out of space and I may erase things. So please pause the videos. So now comes the minimization part, okay? The minimization of the error signal with respect to A, because B is completely done, all right? We found out the optimal value of B. So the error signal right now, oops, beg your pardon, that right now stands at here. First of all, we have a couple of things going on. So we have found out the optimal value of B, but we have not used that to substitute in anywhere, right? So basically, if you expand on this one, you have expected value of X minus A expected value of Y. So that's exactly what I'm going to do in terms of in order to find out the error signal with respect to A. So again, I'm just not doing anything other than just mixing and matching things around. So we have expected value of X minus X hat. So X hat is AY minus B. We have found out the value of B. So this was our expression, right? And that is squared. So what we are trying to do is we are trying to basically, we have found out an optimal value of B. So let's substitute, remember step 3. So one substitution is going on out here. So we will substitute the value that we have found out for B out here. So if you do that, you will actually see that it's expected value of X minus A expected value of Y. So basically, I've substituted this. I've substituted this guy out here. That's it, in place of B, okay? So in order for us to understand what we can do from here is grouping, okay? What we can do from here is grouping. So why grouping? Now people or students, they don't group together stuff and they leave it just like this. Perfectly fine. Again, there is no one right answer or you're supposed to get this answer, otherwise the entire expression is wrong. No, you can just leave it, but I am trying to group it together to make sense of the data, okay? So I'm going to group together X and EX and Y and EY. Why? Well, it might actually be nice for us to start grouping like terms together, right? It might actually result in something. We'll see. So we have grouped this together, right? Minus A of, we have AY. So, well, Y minus E of Y. All right. Now you might completely avoid this step. If you avoid this step, there is absolutely nothing wrong. Again, I have grouped it according to my own convenience. All right. So then we are trying to minimize it. So then comes step 3. Step 3 is, we are still at step 2. My mistake. We are still at step 2. We are actually trying to minimize it. So we are going to equate it to 0 and we are going to differentiate this entire expression. So dA. Now, if you have any other variables out here, you're going to do a d of that variable. So for example, in the first expression that we have for this guy, ay1 plus by2 plus c, after you substitute the value of c, you are going to try and minimize with respect to a, and then you're going to try and minimize with respect to b. So again, minimization of that particular variable means derivative of that variable with this expression. That is expected value of this entire thing, okay? So I'm going to write that expression out and then try to solve it. So again, if you go wrong in the steps, that's fine. I mean, some points will be taken away, but not all of it. So if you expand on this entire term, like it's a square term, remember that. So if you have to expand on that entire square term, you can do that. But I would advise you not to do it and wait for this minimization step to be over. And then you can expand and do whatever you want. So if you basically take a DDA of this entire expression, what will it look like? So first of all, oops, DDA of which expression are we talking about? So the expected value of, we have X minus E of X. Oh my gosh, my mouse use is horrible. I am so sorry for that. Trying to write clearly. Okay, the expected value of X, right? And then you have the expected value minus of A. You have Y minus expected value of Y. Now, at this point, I would try to stop you guys from expanding. Leave it just like this and then equate this to 0. So you have to apply chain rule out here. The chain rule basic formula will be given to you. So according to chain rule, you have to first finish the outside brackets. So the outside bracket is basically your squares. So if you, excuse me, if you have x squared, you write 2x, right? So you're basically differentiated. So basically, you have 2 of this entire expression right? I'm not going to write that entire expression, the 2 of the expected value, right? And then you are going to select whatever variables are there in A, and then you're going to differentiate that and write that, right? So the chain rule works in this way. It moves through the expected value operator, all right? Now I'm explaining you the nitty-gritties. It moves to this operator, goes out here, goes past this one, and first encounters the square because that's outside the bracket, right? It's outside the expected value operator. So once you encounter this guy, you first write, x square equals, like if you differentiate x squared with respect to x, you have 2x. So 2 of this entire expression multiplied by, okay, now the expected value operator, again, that outside square is taken care of. Now the DDA kind of moves inside. Well, doesn't have any A operators out here, but comes across this one. So so DA over DA and multiplied by this guy. So DA over DA is 1. So this guy comes and sits here. So what are the two expressions that we have? The one expression is that this one is the entire e to the power of x just sitting out here, the entire expression, right? This is the entire expression sitting out here. And just whatever is there inside this bracket is sitting out here, okay? So I'm going to erase this screen because I don't have any more screens left. So, and I'm going to start again a little bit because I ran out of screens. So I'll tell you exactly what it looks like, okay? So you first differentiate it and then equate it to 0. And you're trying to basically find out the value of A. Okay? Again, this is already a part of your homework solutions. So if you are confused, you can go and take a look at that. So you're trying to find out the value of A, okay? So if you do that entire step, you're going to come across something like this. 0 equals, now I have to do it, hang on. This is squared, so this is 2, no, hang on. Hang on, just for 1 second, let me work it out for myself. So this is 2 expected value of x minus e x minus a y minus e y. Okay, now that gets ended. There's a minus out here, so this goes minus. And then what we are going to do is we are going to multiply y minus ey. Like you have to just work it out, I mean, at this point. And then the expected value operator closes. The 2 multiplication closes. And then you operate that to 0. So if you actually work out and try to find out the value of A from here, you'll end up getting A equals, I'm going to set that to 0. So expected value of x minus e of x multiplied by y. Actually, I made a mistake. Hang on. This bracket should not be closed. Okay. Multiplied by y minus e of y. Now the expected value operator bracket closes. Okay, so I should not be putting in. It's just me working out, guys. So give me a little bit of time. Yeah, that times that, okay, divided by or upon, you have the cross multiplication part. So y minus, oops, so sorry about that, expected value of y minus e of y. Again, you might not get the same result. So if you do not, don't panic. Basically, y minus ey whole squared. That's the point. If you don't get this, again, if you don't get the same expression, that's fine. Perfectly fine. Whole squared. That's exactly what we are going to get. So, I mean, if you don't get this kind of A star, that's fine. All right. I'm going to erase some parts of the previous problems, and I'm going to show you why we have basically grouped these two things together. Okay. So the grouping, again, it's not essential. And if the problem is a bit bigger, you might actually struggle with the grouping. So do not worry about grouping the entire variables together and getting a neat equation. If you cannot, please skip it and give me the basic big expression. You're still going to get the full points. All right. So quickly going forward. So we have A star. Now, if you actually look at the formula for your covariance and variance, you will see very easily that this is the covariance of xy, because that's exactly the expression of that. And this basic part is the variance of y. Now from here, you can take this a step further and you can give me a neat expression with just the correlation coefficients. All right. Again, you need not do this. If you cannot do it, don't. If you can, great. All right. So again, if you have to see the expression for, yes, please keep it. If you want to see the expressions for these guys, you are more than welcome to go and study this, the covariance of x and y. The covariance of x and y is given by various formats, but the basic format is e minus e of x, y, x minus e of x, y minus e of y, and the whole expected value of that. And then you already know that the covariance upon the variance, that is your correlation coefficient. So you might or might not actually get this neat expression, which is perfectly fine. Again, don't worry about it. Your basic job is to do it correctly. So now, once you have the optimal values of A and optimal values of B, what you need to do is to basically substitute. So this is step 3. Right there. So substitution is basically you're putting in the x hat, you're giving in the A star y plus B star. So again, this is just a couple of points. So don't worry too much if your expression is very big. No need to panic or, whatever. So again, if you can just write the very big expression or the smaller expression that you have. I'm going to use the smaller expression just for the sake of time. And then you have the B star as well. Don't forget that, because the B star has been found out by you, remember, in your previous expressions out here, that when we were trying to maximize and minimize and all those things. So I'm just going to use those expressions directly out here. That is the expected value. I mean, you can play around with this entire thing again, but the expected value of x minus a expected value of y. Again, you can just rearrange it and whatever, So this is the entire expression. So what are we trying to do out here is to basically find out the optimal values of A and optimal values of B, substitute it in the equation, and just give the expression. But look at the question. It does not tell us anything about these steps. From the first principle, derive the expressions of A and B. That's given. You're not given what type of expressions of A and B, whether it's an optimal expression or what. And then estimate where x hat is basically an estimated value of x, and you have to use the minimum square estimate principle. So these steps break down where you are going to basically, how you're going to tackle the problem. And as you can see, the error, once you find out the error, that's your 2 points or 2 or 3 points there. The minimization of A and B is basically the majority of the points. And then once you put back the equation, it's not really a big deal. So that's going to have 2 or 3 points again, depending on the weightage of the entire problem, right? So if it's a 15-point problem, I would assign, if I were you, and if I'm having rubrics, I would assign 2 or 3 points for the first point, 2 or 3 points for the second. The majority of the 10 points may be for the basic minimization steps. All right. So I would say for this one, sit and practice one type of problem. If you're comfortable using x hat as ay plus b, great. If you're using ay1 plus by2 plus c, great. Whichever works for you. But there's a type of, like, there's a flow to the entire problem. Don't mess around with that flow. Okay. So the next part is basically this guy. Now, this guy, we don't need to talk a lot about it because I know that there are students who have solved this successfully. Most of you have solved this successfully, but again, after the exam was over, I got maximum questions for this problem somehow, um, which was surprising for me. Out of all the other problems, this was the one that was creating a problem. But yeah, so let's actually try and see where we can, first of all, these type of problems might not be there for your exam, but then, I mean, it could be there as well because, Dr. D might actually wish to put it. I would rather, if I were you, practice the bigger problems that you have. For example, this one. This one is again straight from your exam. Um, Most of you again have made perfect entry and, a little bit here and there, a little bit here and there, but most of you have got this entire thing right. But we are going to talk a little bit about the footprints, and some of us have not exactly captured the essence of that. So if you are not too sure about the footprint, then what kind of problem it can create for us, that might be an interesting problem for us to solve. Other than that, if you are again not sure about any of the problems from the midterms, please come and talk to me. I'm available at, as you can see, anytime. Um, so apart from that, I'm not going to drag this entire problem sessions for too long. So quickly going over this guy, and these are again the different types I'm giving you and the rubrics. So for this guy, what we are going to do is we are going to quickly go over what the entire problem entails and where how we can start solving it and stuff like that. So what we can do now is we have fy of y. That's a question mark, right? Um, so what we can do is there's with the problem with these problems is that given fx of x, now there is no fx of x, right? We don't have anything in the fx of x. We don't have it Gaussian or anything. So when we say given, it's very confusing for us. But if we say that, okay, suppose let's assume that we know fx of x, okay? Okay. What happens if you know fx of x is that let's actually point out, okay, where we went wrong or how we can even go about solving this problem. Now, I actually requested Dr. D not to introduce these kind of problems, but then what he was trying to test you was on a very basic step. And that basic step is the concept of the very basic concept of CDF and PDF in the definition in itself, right? So what is the definition of PDF? It's basically the differentiation of CDF, right? So if you are trying to find out for Y, you have to basically target your FY of Y first, right? And what is the basic definition of PDF, CDF? CDF, you can define any other CDF as Y less than Y, right? These are the only two things that we know from the book. So basically, whatever you get from the CDF, you differentiate that and we get the PDF. Now for fx of x, we don't have either of them as well. But what can we do if neither of it is known and we have to still solve the problem? All right. So we'll start with whatever we know already. So I think that's where students got a little bit confused. So this is basically differentiation of fy of y, right? And where do we find Fy of y? Well, we don't have Fy of y either. Oops, and that is not the correct way to express it. I'm so sorry. Again, I'm not going to spend too much of time with the concept of this one, but F capital Y of small y, how do you define it? That is probability of capital Y, which is the random variable, less than some value. And this is the very basic definition of probability. If you can actually work around this specific definition, because that's all we have, we can basically substitute 3 minus 2x less than equals y. And then what do we do? Well, we're trying to actually get to the random variable x. Why? Because they have told us that given fx of x. So let's assume that x is known, right? So if you assume x is known, then probability of, well, you have to subtract 3 from both ends. So you have 2x. A lot of you have gone wrong with the equality operators as well. So I'm going to break it down, right? 2x, and we still have y minus 3, right? And then you have probability of, well, you have a negative sign on both ends. So keep that negative sign as long as you can, without flipping it. You know how the operators kind of work, right? So now when you have a negative sign, you know that if you actually want to get rid of that negative sign, the expression kind of flips. So what do I mean by that? Is that if you now multiply, suppose -1 on both ends of this expression, that is this end and this end, you have to basically change the um, operator. That is, you have to take it as greater than. That's great. I mean, there's no panic in that. So y minus 3 divided by -2. Now, uh-oh, well, we have something greater than. Well, that's not a problem, right? So because we have 1 minus, you can easily flip this expression by saying 1 minus x less than y minus 3 divided by -2. Now you have the expression completely. Now you can take the differentiation of this entire expression with respect to y. With respect to y, you know that the first expression, so take a differentiation of this one. If you differentiate 1 with respect to y, that's a 0. What about the next differentiation, right? Well, you have, so you can basically call this fx 1 minus fx of y minus 3 upon -2. So now you're differentiating fx, right? So what does it look like though? So we are differentiating with respect to y. So let's write, first of all, chain rule again. The outside brackets, so chain rule, when I say chain rule, what do I mean? The outside is going to get differentiated first and then the insides of the brackets. So the first part is fx of x, right? So differentiation of that gives you the small fx, right? And then you differentiate the inside of the brackets. You have y. So differentiation of any constants, you have y minus 3 upon -2. You will have like -2 out here. So 1 divided by -2. And this actually, if you calculate that, so sorry about that minus. If you just like solve that, you'll have basically half f y, oops, sorry, fx of, not fy, fx of y minus 3 by -2. So that's exactly what he wanted. But what he was checking for rather is the very basic concepts of how you deal with CDF and PDF. So again, if you have more confusions on this problem, we can always talk about it later. But we are going to move on to the, again, this particular question. If you see your final exams, yes, please keep it. If you see your final exams, wherever I have it, like the majority of it is basically your CLT will be like, one majority is obviously your statistics problems. That's 20 points. The other one will be your estimates, sometimes 50, sometimes 20, depending on how complicated the expressions are. Honestly, I would give 20 points to this one, but anyway. 15 or 20 points depending on how complicated your CLT is. So this one is also going to be one of the good weighted problem in your entire exam. So might as well get that right. All right. So again, for probability, know one good problem. Whichever problem you are comfortable with, I am going to do this problem because this is very easy for me to explain. This is also there in your homework, as well as you can very easily, I can very easily explain you the rubrics, which is the main point of this entire exam review. So we start with how to solve the problem, and then we are going to go with the nitty-gritties of the rubrics and all the other etc. Right? So this particular part of the problem, you have to understand that there are 3 to 4 steps again. The first step is to find out whether you know the mean and then you know the standard deviation, but then let's call that variance. So mean and variance should be known in the problem. All right. Once the mean and variance is known, you're going to try and find out what the problem exactly wants us to do, right? Sometimes it will be like, okay, find me greater than some values, find me in between two values, find me lesser than some values, right? So here we have in between, all right? And then again, in between. Sometimes the values might be greater than or less than, right? So take care of that after the mean and the variance is known for the problem. So then we have different steps. One step is to basically, once you know that, let me actually write down the steps. Sometimes people appreciate that. And these are the different steps on how, again, the rubrics are going to work. So step one is basically your mean and variance, okay? So this step is again going to have 2 points to it. If the mean and variance is already mentioned in the problem, then this step points are going to go somewhere else. Out here, you have to find out the mean and variance. That's why you have 2 points for that. The second step is to find out the expression itself. That is the CLT expression. Okay. And you'll know what I'm talking about in a while. So the CLT expression. And then the third steps are, there are a couple of steps. So first of all, you have to find out the phi of x. All right. It's going to go exactly according to the Gaussian problems that you have solved in your first exam. And then you have to find out the q of x. All right, once you find out the phi and the q of x, your step 3 is done. Step 4 is look up. Look up and calculate, basically. Look up and calculate. So this is how my rubrics works. But I'm going to stick to look up because sometimes looking up the values are enough. Sometimes you need to calculate it because, they are not that straightforward. So we'll see. So look up plus calculate. So again, majority of the problems are going to be in finding the expression. So again, for example, if this is 20 points, 2 points for this one. Look up and calculation is 2 plus, I would say 1. That's how less important this is. So 3 and 2 is 5. Majority of your like 15 points that are there, I would say this is 5. And unfortunately, this is all your majority. Even if it is just the expression part of it, how you form the expression is very important. And then how you are going, because the step 3 and the step 4 and kind of the step 1, we are used to this from the first exam. But how the CLT is getting formed, that is important. So first of all, step 1. Step 1 is basically a fair coin is tossed 100 times. So n equals 100. Great. A fair coin is getting tossed. So what type of information is that one? So this is basically a binomial, right? A binomial random variable. So why? Because this is a coin toss experiment. Either it can have heads or it can have tails, and the probability of the heads and the probability of the tails, that is basically half, right? So it's like a on, off, yes, no kind of a situation, right? Now, great. So we know the probability of heads and tails, it's half. We know that this is a binomial random variable. Can we find out the mean? The mean of the random variable, if you look at the back of your exam, it's going to be NP. So NP is basically 100 times half, which is 50. What about the variance? So the variance is going to be basically, there's a formula for that, NP 1 minus P. Now I know that because I've done this problem session like 100 times, but the point is you have to basically look it up. And this comes out to, let me just calculate that one, like for one thing. This is 50, 50, 50, 50, 25, right? Yeah. So that. Now what we have is the second part. All right. Before going to the second part, we have to actually find out it's in between. Okay. So a fair coin is tossed 100 times. Estimate the probability that the number of heads, so we are calculating for the number of heads. Okay, great. Is between 40 and 60. So when I form the expression of that, 40 is going to be at one end of the spectrum, 60 is going to be at the other end of the spectrum. Now, what are we trying to find out is basically this. What we are going to do out here is going to depend on two factors. What is the mean and what is the, well, I would say variance, but I mean the standard deviation ultimately. So the expression can go like this. Whatever is our value that we are trying to find out, we will subtract the mean from that and we'll divide it by the standard deviation. What is the difference between variance and standard deviation? Well, variance, if you take a square root of that, it's standard deviation, right? So this is standard deviation. Do not confuse that. What we have found out is the variance, not the standard deviation. We have found out sigma squared. Remember that. This is where, again, student makes most of the mistakes. This is sigma and this is mean, by the way. This is mean M and this is sigma squared. That is the variance. So whatever you do to the values out here, it's kind of going to actually replicate for the values at the extreme ends as well. What do I mean by that? So let us find out what we have already. We have N, right? We have the mean, that is 50, and we have sigma. This N basically is the event. So estimate the probability of the number of heads. So let's say number of heads is N. So whatever event is that's going on, that's basically represented by the big one. Minus M means, well, you have to subtract mean from both ends. That is 50. That's kind of static, right? And we have to divide that both. And I'm doing this very mechanically. Obviously, there's a logic behind this, but again, so that you don't go wrong in your exam. And upon sigma, sigma is 25. Now remember, variance square root, okay? Variance square root. Why? Because that's sigma. Otherwise, it would have been sigma squared. All right? This expression, when you come up with this expression itself, you're going to come up with some sort of values, right? Because you have to work this 40 minus 50, whatever that is. So you're going to come up with something. Hang on. Is this minus 2 or am I dreaming? 40, 10, 10. Yeah, this is minus 2. Minus 2 less than N minus M over sigma. 10, 10, 5, 2, right? All right. So this is exactly the expression for your second step. Okay. Now from the second to the third step, the transition from that, I'm so sorry, I forgot to mention the probability. Oh my gosh, where's my mouse? Oh, there you are. I forgot to mention the word probability. So sorry for that. Now, for our case, we have step 3 and step 4. this is exactly going to go as you have done in your first exam. Okay. Now you're going to understand why I did not directly write the expressions of Q. Now, Dr. D directly writes the expressions of Qs. Now you're going to write, understand why I did not write the expressions of Q directly. Now, from this probability curve, what we have out here is that you have phi. So this you can write phi of 2 minus phi of minus 2. And again, this is all a part of your formula. If you are confused with that, I can basically, again, go over them. Come to me in my open office hours whenever you want. So this is your first minus your second, all right? Whatever the values are inside the brackets, okay? If you have only one expression that is greater than, less than, whatever, process that. But here, since you have a limit, you have to subtract. So phi of 2 is great, but what about the phi of minus 2? Remember, the expression of phi and q, 1 minus q of x is phi of x, right? So you can either convert that entire expression to q first and then convert everything else, like we practiced in the first exam, or do it in your own way, all right? So the phi of 2 is 1 minus q of 2, right? Now this one is already, so 1 minus q of 2, right? But this is q of minus 2, right? So instead of q of minus 2, what we can write is the q of 2 part, right? So instead of q of minus 2, what we can write is 1 minus q of 2, right? So this is like a very complicated expression. In fact, if you work this entire thing out, you're going to see that you're going to come up with q of 2 again. So instead of this entire big expression, I'm now going to substitute that with q of 2. Right? So first step is convert this into q of 2. Second step is convert the minus of the inside braces into your, so use the formula q of minus x is equals 1 minus q of x. So you're using that formula twice, so you end up with a positive value of q. So this is basically your 1 minus 2 of q, right? Okay, this is equals, I mean, pretty much out here, you can substitute. Now you're moving on to your step 4. You're going to look it up and you're going to solve the expressions. And that's basically, so the third part was this q of x and phi of x and all those things. And the fourth part is basically your lookup, right? So anything beyond this step, look it up, solve the expression, anything apart from that is basically your step 4. So again, remember that the last step contains the least amount of things. You have to concentrate on building your expression for the CLT and then how you're dealing with the phi of x and q of x. That's your entire problem set for CLT. Doesn't matter even if it's given greater than 40 or less than 60. It's the same format for any of those. Same rubrics, basically. All right, let's move on to our one of the last problems that we have. We are going to work with this one. Now, this might or might not have been actually done in your class. So this one is actually easy to work out with. But what this basically is and why we are going through this is of two reasons. The first is that this is basically called as Jacobian. Now, I know that some of you have, if you go through your lecture notes, you might have actually come across this transformation. So this is called Jacobian. And these problems have been assigned in your homework 7. All right. Why are we learning this is that this is one form of transformation. All right. Remember in your project 2, when you went from your colored scale images to your grayscale image, that is one sort of transformation that we are doing. We can definitely transform it back, but the expressions for that transformation is also going to be a little bit, interesting, different. The other very interesting example for transformation is that when we go from spherical to cylindrical, cylindrical to back to, etc. So those different types of transformation, it's very common as you now can understand. So this is again one sort of transformation or rather projection. Sometimes if you take data in your frequency domain instead of the real time domain, you find that some of your expressions have simplified, some of your graphs and plots have actually simplified. So again, transformations are required for simplification purposes. That is why as an engineer, you are supposed to know Z-transform, you're supposed to know the Laplace transform, you're supposed to know Fourier transforms, right? So again, that is why this kind of transformation is introduced for our syllabus purpose. Not sure whether this problem is going to be there or not, but looking at the trends of exam 2, I'm not going to leave any stones unturned. So we are going to do one of these problems. This problem is exactly from your homework. I'm not saying or suggesting that this is going to be from your homework, but I'm going to give you the steps and the rubrics. So there are a couple of steps for this problem as well. So you find out that, well, you have and I swear this is the last problem because I know that the clock is kind of ticking. So, oops. Nope, that's not exactly what I'm trying to do. I am so sorry for the confusion. Yes. So step 1. So step 1 is basically you find out expressions. So you have f of xy basically, but instead of x and y, we have x1 and x2. Great. So if you have different types of variables, don't get confused, right? It's still the same thing. It's functions of 2 random variables or just 2 random variables. It's fine. So the expression is E of x1 plus x2. Now, if you have observed your mathematics part of it, you have to basically work with indices. You have to work with chain rule for differentiation. You have to work with integration. So basically all your basic level math is always tested in probability. That's why it sometimes gets a little bit difficult for us, Yeah. So sometimes you'll have logarithmic expressions as well, which gets a little bit easier for us to work. But again, you have to know the law of logs and everything. Anyway, so now what we have out here with us is 2 expressions. We have something in x and we have something in y. So what we are trying to do is to convert from this x domain to this y domain. Okay. So now out here we have x1, x2. And here we have y1 and y2, okay? It's very simple, actually. It kind of looks complicated because some of us might get, confused with what are we doing out here and why we're trying to solve this problem. But it's actually very simple. So let's actually try and first figure out what we can do with this particular expression. So the first part of the problem is to convert. So the first part of the problem is to figure out, okay, this has no points to it. Like this is the first part of the problem, but this has no points. The points really come from step 2. So step 2 is basically you have y of 1 equals x1 minus x2. And then you have y of 2, which is, where is my x of 1 plus x of 2, okay? So these are the 2 types of problems you have. Your second step is to convert this expression in terms of TERMS terms of x1 and x2. Now, what do I mean by that is you have to find out this is y1 and this is y2. Okay? Solve simultaneously. Oops, that's not exactly what I'm trying to do. And I'm not going to actually exactly work this problem out, but since this might or might not be there for the exam, but I'm going to give you the steps for it. Now solve simultaneously. And this also is, if you want to actually find out the exact expressions for this, this is already there in the solutions. So solve for x1 and x2. So this is your expression 1. This is your expression 2. Solve them simultaneously to get the values of x1 and x2. This is your second step. Okay. Your third step is to write down the expression. Okay. And Jacobian problem, again, let me see if it's there as a part of our final exam thing that we were doing. It might actually contain just 15 points or 10 points, honestly. Yeah. Oh, it contained 20 points. All right, well, so it depends. But I wouldn't worry too much about it unless like I don't know anything how to solve it. Sometimes students just need like that boost, that how to even start the problem. Okay. So solve for x1 and x2 is the first step. Please write it down even if you are studying like multiple subjects, because these are the things that are going to be required in your exam hall. How to actually go about solving it. How to solve for x1 and x2 in simultaneous equation, I'm pretty sure everybody will be able to get that. The step 3 is basically to find out. So now that you have the expression for x1 and x2, what we are going to write is fy1 and fy2 in terms of x. So in terms of x, what do you mean by that? In terms of x1 and x2. So how do you exactly do that? How do you do that is like this. So f of y1, y2, y1, comma, y2 is equals f of x1, x2, x1, comma, x, oops, that's not y, my bad. And x1, comma, x2. So what you're going to write is in terms of, since you already found out the expression of x1 and x2, in terms of y, say for example, if I really quickly solve this one, let me actually see if it comes out. I mean, I might be like horribly wrong, but I'm trying to actually make some sense of this entire thing. x1 plus x2. So the first x1 is basically, oops, where's my pen? Oh, never mind. It was at pen. So f of x1, x2. So you're giving the expression for x1 in terms of y. So y1 plus y2 upon 2. And again, I'm trying to solve for x2. I think this is going to be like x1 minus x2 or something. I'm not sure. This is probably y1 minus y2. I'm not sure. Just calculate that, and I'm just going to give you an expression for this one. All right. So anyway, the main point is that this is not changed, but these variables are changed. Okay. And I'm doing it extremely mechanically because again, I'm worried about you scoring. Understanding part, again, you can come and ask me 1,000 questions. I don't care. So the first step is find out the expression. Second step, solve for x1 and x2 simultaneously. Third step is to substitute. So this is your substitution stage. Once your substitution stage is over, you have to write the expression correctly. What type of expression? Now, Fy1, y2, y1, y2 is not only just f of x1, x1, x2, there's a Jacobian matrix that gets multiplied along with this guy. Now we are going to try and find, so this is the entire formula, all right? So f of y1, y2 is the Jacobian matrix, which we are going to try and find out, of y1 and y2 multiplied by this expression. So the step 3 is correctly over. We move on to step 4. Step 4 is to find out the Jacobian matrix and take a determinant of that. How do you find out the Jacobian matrix is as follows. Jacobian matrix basically starts with your expressions in itself of x1 and x2. So say, for example, according to my 1 second calculation that I did, I might be wrong, y2 upon 2, and x2 is basically, again, I am just giving rough estimates. Please do not call me out on this one. Solve it by yourself. So what you do in the Jacobian is that you take this x1 and you take this x2, okay? Again, x1 and x2, and you differentiate that with respect to the variables that you're trying to find out with. So for example, y1. Again, you differentiate that with respect to the variables that you're trying to find out, y2. Differentiate that with respect to, oops, sorry, that's not, my bad. That's y1. So again, this Jacobian matrix, unfortunately, will be, fortunately, obviously, given at the back of your exam, but it might not be exactly catering to your problem. It might be given in a generic format. What you have to figure out is how to use this if this problem at all appears in your exam. So there's a very easy way for me. Again, this is my formula. Anything that sits on your vertical axis, these are your variables that you already have. Anything that sits on your horizontal axis is the variables that you need. Oops, sorry, no, my bad. I said the exact opposite. So anything that sits on your horizontal axis is basically what you already have. Oops, sorry, yes. So this exactly is, anything that sits on your vertical axis is what you exactly already have, x1 and x2. And anything that sits on your horizontal axis is basically your y1 and y2. Now, sometimes you might get expressions in v and w and x and y, all right? Sometimes you get x1, x2, y1, y2. So don't get scared if this set of things varied. Again, if this problem at all comes in. So basically what you need to do is prepare the Jacobian matrix. After you prepare the Jacobian matrix, obviously you have to solve it. So differentiate x1 with respect to y1, you have 1. Differentiate x1 with respect to x2 with respect to y1, again, you have 1. Differentiate x1 with respect to x2, you have, I don't know, according to my thing, minus half. And again, x2 with respect to, no, actually you have half. This is half and minus half, whatever. So that values again is not very important for me. So you have to take the determinant of 1, 1, half, minus half. Again, don't call me out on these values. Please check on your own. You take the determinant of that. If the determinant comes out to be 0, that's great. Do not panic. Sometimes the determinant, usually it does not. It will have a very specific value. But if it comes out to be like nothing or something, don't panic. So after you find out the Jacobian matrix and you take the determinant of that, the final step is to put back all these in the expression in step 5. All right. Step 5 is basically just put back the expression saying that f y1, y2 is basically f of x1, x2 multiplied by the Jacobian matrix, so minus minus f of x1, x2. Write the big expression that you have. That is your y1 plus y2 over 2 and y1 minus y2 over 2. All right. So this is the final expression. You don't have to solve. Sometimes you want to solve around and play around with it. Doesn't matter. Once you get step 5, you're going to get the full points. A couple of things to remember out here is that the majority of the points for this particular problem will lie in the fact whether you can come up with a valid expression for step 3 and step 4. So 3 and 4 will have maximum points in this. Step 1, there's no points in that. Like it's just the expression. Step 2 will have maximum 3 or 4 points depending on how complicated the expression is. 3 and 4 will have maximum amount of points for it, and step 5 will have just 1 point. So these are the different types of problems that you can get. Apart from that, this problem is also definitely some variations of that is definitely going to be here. Either you can get it in as simple formats as this one, like this guy. I am pretty sure that this is not going to be that simple. So we are going to practice this part as well, because if you again, if you're confused about drawing the footprint, right? So good question is that, okay, first of all, what is the footprint of this one, right? So let's actually try and do that, because some of us, I mean, not a lot of us again, but some of us have gone a little bit wonky with the diagram. So you have x and y axis. So both extend till infinity. So do not restrict yourself in just one dimensional diagram. You have to put in your minus x out here as well. You have your minus y and etc., etc., So this. Now you have certain value between 0 and 1, which is great. Now you have a range, right? So your 1, the range of 1, unfortunately, is here, right? So nothing can go beyond this one. Or let's see. Okay. So you are traversing, your x is always less than y. So first of all, in order for us to be less than y, what if we actually find out what if x equals y? So x equals y or y equals x. Oops. Now this is going to be very difficult for me to draw a straight line. All right. So this is y equals x, right? This is the straight line. Now this is a horrible diagram, so I'm going to just start over again. So the basic, I think a good starting point for us would be to basically see what this expression is trying to say us. So the maximum point is a straight line. So this is y equals x. Now we can say, okay, all the x can either be here or either be here. So if x is varying faster than y, x is greater than y. If x is varying slower than y, then x is less than y. So that is why it is this region. Because this region is always for x which is varying faster than y. This is always the region where x is varying slower than y. So that's the footprint. Now, for example, I'll do another one because the footprint kind of is an issue for a lot of other problems. Remember that you also had a problem in your, oops, that's not what I want. Okay, it's there. So you also had a problem like, where the CDF was given to you. Okay, that's there. So the CDF expression was given to you fxy of xy. It was some kind of, I don't know. I have to just look this up. Hang on. It was 1 minus 1 over x cubed, something like that. I'm just remembering from, my faint memory. All right, don't again call me out. So the expression for this one was like this. And the region of interest was given x greater than 2 and y greater than 2. Okay. As soon as you all saw greater than, everything died. Why? I'm not sure. Well, what does this mean though? The part A was just to solve for draw the footprint and find out fx of x, fy of y, blah, blah, blah. So fx of x is basically the marginal density for marginal CDF. I mean, I can find that out if you want, but let's concentrate on the footprint though. So the footprint is very simple. The footprint has nothing to do with the problem, right? Just look at this expression for the footprint. So you have, again, x and y, right? So this is y, this is x, and you have a 2 out here, you have a 2 out here. So you immediately form your lines, right? So now x greater than 2 and y greater than 2 is immediately in this zone, right? Doesn't matter if your problem is suiting or not, it's fine. This is your region of interest. That's all you had to mention. And then you can go ahead and, do all your fx of x and fy of y and all those other things. But then that's the point. So let me see if there is any other region of interest, because the region of interest created a lot of problems. Sure, why? Yeah, so this is another problem that we had. So let me see where we can accommodate this one. Okay, let's see. So we had another problem where fxy of xy was given to be c e raised to x plus y, and the region of interest was this is an interesting problem on why. I don't know why Dr. D gave it this way. X greater than or equal to 0, y greater than or equal to 0, and then he also gave in this value saying that it's 0 less than y less than x. I completely forgot, so I'm just going to write I'm going to write 1 because I don't remember it exactly. Anyway, so now the point is that you have to find out this region. I mean, the best part for us is to close our eyes and eliminate this option. Why? Because if you eliminate this option, well, 0 is less than y, 0 is less than x as well. So obviously y and x is greater than 0. There is no doubts on that. So let's eliminate the unnecessary options that we have in the problem, right? And go with the necessary steps. So the necessary steps is to first of all draw the footprint. Now for the footprint, so the second expression is important for the footprint. Remember that y equals x is our line. So now here the y is traversing, the y is less than x again, right? So for some parts you needed to actually consider that this is, so y is greater than x, or x is basically greater than y. So now from here, where's my mouse? From here, from this expression, can you guess which region of interest this one is? Once you have x is greater than y, and the other one you have x less than y. So of course, you are bound by the lines of 1. You cannot go beyond 1. So either it's going to be this side or it's going to be this side. So if you have y, which is variating slower than x, it's this region. If you have x variating slower than y, it is this region. So again, just that's the footprint. Now, the important part in this entire expression is that why is it important for us to actually have the footprints in the first place? There was also, I think, this problem itself also had footprint. So let's actually draw the footprint. Okay, I have already drawn the footprint. Never mind. But yeah, the point is that why is the footprint even important? What happens if the footprint is removed though? So if you remove the footprint, nothing is going to really happen. It's just that this entire PDF, the concept of the PDF and CDF, the integration limits is from minus infinity to infinity. If you don't stay bound within a certain region, you're going to work with minus infinity and infinity. For this specific types of problem, minus infinity and infinity is great because 1 over infinity is 0, right? But for this type of expressions where you have k x squared y squared, well, we have to deal with infinity squared, infinity squared. Well, that is why we bound it to a certain region. And in real life as well, like if you have a function which goes on for eternity, you bound it within some confined x, y, and z, or x, y, depending on what type of signal it is, and then you try to find out the characteristics of that signal. So that is why it's important for us to find out the footprint and how that function is variating within that specific region of interest. So what we are trying to find out is, where is my mouse? This is basically the region of interest. It's also called the region of interest. This was actually one of my focal points in my research work, but yeah, this is the region of interest basically. Yep. So other than that, I mean, I'm not going to completely solve this problem. If you again want me to solve the problem personally in a group, whatever, whichever settings, come and talk to me. Other than that, I'm not going to basically drag this session any longer. I'm going to upload the slides if you all again require it, but please concentrate on studying statistics, concentrate on chi, t, and z distribution. Out of that, z distribution is the most important. Chi and t will, one of the two will come, but z will be there. Okay. The second point is CLT. CLT, again, stepwise, how the rubrics are basically getting across. You kind of know it now. Try to find out the very basics of, wait, where's the problem? Yeah, try to find out the mean and the random variable if it's not, I'm so sorry. Try to find out the mean and the variance if it's not given. Then you have the expression for the CLT. Then you work around with your phi and q distributions, and then you look it up. The next one is your Jacobian. If it comes in, you have the steps in front of you. You have to first of all go over and try to find out the expression for x1 and x2 or z and w or whatever is there. Take that in terms of the given variables, and then from there calculate the Jacobian matrix. From Jacobian matrix, go on and substitute. If these kinds of expression come in, please actually don't go wrong with the footprints. If you're not actually aware of the footprint, sometimes what happens is equate this one. Like if it's a very complicated expression, equate this one. Like if x is equals y, then what kind of geometry is that? It's a straight line that follows the origin. Now x is later than y, less than y, then what type of graph? X is greater than what type of graph? That sort of things. So best of luck for your exams. I'm going to stop sharing. And if you have any questions, again, please let me know anytime. I'm available all throughout the clock. Whenever you see me on Teams is when I'm basically alive and working, and you can ask me. Any questions, concerns, let me know. All right, guys, best of luck.